Hello MacroHeart community, welcome back. So today we are going to discuss about a new design to store the underlying database of a blockchain. So we all know that blockchain has several accounts and each account has data which includes the balance and the code and the state of the code. Now with time it's becoming more and more expensive to store this underlying data of the blockchain. And since this data is immutable, this state is ever growing. So which means that in future, only those computers which have a huge memory capacity can only validate the blockchains. And this is not good because we want to reduce the barrier in order to validate a blockchain as less as possible. So this new database structure is called a vector commitment scheme. Sometimes it is also referred to as Verkle trees as opposed to the conventional Merkle trees. So to understand vector commitment schemes, let us assume that there is an array of data and this array has an index and the corresponding value. Let us assume that this array has a size of 1000, and another thing that we need to understand is a commitment for this array. So commitments are one-way function, which means that if I have an array, I can produce a commitment, but if I have a commitment, I cannot produce an array. So intuitively, this can be thought of as a fingerprint of an array. So the good thing about commitment is that it is a very cheap data value. Now, as a cherry on top, another good thing is that suppose I have the commitment of an array, although I don't have the underlying array, and Alice has the commitment as well as the array, then if Alice wants to prove that the 10th element of the array is, let us say, 1024, then Alice can create a proof that the 10th element is 1024 against the latest commitment. Now, since I also have the commitment, then I can use that proof given to me by Alice and I can verify that proof against the commitment that I have. And using this, Alice can prove to me that indeed the 10th element of the array is 1024. So this is the good thing about commitments, that they help you to generate proofs for the elements of the array. Now the next problem that comes is that how can I update the commitment of the array without actually having any information about the array? Now here a special property called homomorphism is leveraged in order to update the commitments. So this property says that if I have the commitment of an underlying array and the 10th element of the array increases by 1, then I can update the commitment by using the previous commitment and by using the fact that the 10th element of the array is increased by 1. Note that I still don't have any information about what actually is the value of the 10th element of the array or any other element of the array. So therefore, as long as I know the change in values of the array and I have the current value of the commitment, I can keep track of the latest value of the commitment of the array. Now the picture is complete. This means that I can create the latest value of the array if I know about all the transactions in a blockchain. For example, if Alice sends 1 Ethereum into Bob's account, then I still don't have any idea about the balance of Alice or Bob. But since I know that the change in the account of Alice is -1 and change in the balance of Bob is +1, I can update the value of the commitment accordingly. Since now I have been able to maintain the latest value of the commitment, if the miners of the blockchain also attach the proof of balance of the users that are interacting inside the transaction, then I can actually verify the transaction without having any information about the underlying array or the state. This means that I can verify the whole blockchain transactions without actually having access to the big fat state of the blockchain. And maybe I can do this on my mobile phone. And this actually enables something called stateless clients, which we had discussed in one of the previous videos. And this again reduces the barrier of entry for anyone to validate the blockchain, because again, your device doesn't need to have a big and fat memory access. So that's all for today. If you find this video enjoyable and insightful, then press the like button. And if you are new to this community, then subscribe to Macro Hard, where we are building the next economy. So see you all guys tomorrow. And until then, take care and bye-bye.